Picture the universe in its earliest moments, a vast, silent darkness, untouched by the light of stars. This was the cosmic dawn, a time so ancient it feels almost mythical, yet it's the very foundation of everything we see today. For decades, scientists painted a picture of this era based on theories and models, believing they had a grasp on how the first stars and galaxies ignited. But what if everything we thought we knew was wrong? Recent discoveries have ripped through those assumptions like a supernova, revealing a universe far more chaotic, mysterious, and breathtaking than we ever imagined. This isn't just an update to the textbooks, it's a complete rewrite of cosmic history. Think about the boldest ideas you've ever heard about space, the birth of galaxies, the role of dark matter, the way light first pierced the darkness. Now, imagine all of those ideas being turned on their heads. That's exactly what's happening right now in astronomy. Cutting-edge telescopes and groundbreaking data are showing us that the cosmic dawn wasn't the slow, orderly process we once believed. Instead, it was a turbulent, explosive era where the rules of physics played out in ways we're only beginning to understand. Some of these revelations are so shocking, they've left even the most seasoned researchers speechless. And today, we're going to explore 28 of these shattered assumptions, one mind-bending discovery at a time. What makes this moment so extraordinary isn't just the science, it's the humbling realization that the universe still has secrets we can't even predict. Every time we think we've uncovered its mysteries, it throws us a curveball, reminding us how much we have yet to learn. This video is your front row ticket to that journey of discovery. By the end, you'll see the cosmic dawn in a whole new light, not as a distant, abstract chapter in cosmic history, but as a living, evolving story that's still being written. So buckle up, because we're about to dive into the deepest questions of existence, and the answers might just change how you see the universe forever. For generations, astronomers envisioned the cosmic dawn as a slow, almost lazy awakening, a quiet transition where the first stars flickered to life one by one across the vast emptiness of space. But the universe, it turns out, has a flair for drama. Recent observations from next-generation telescopes like the James Webb Space Telescope have captured something astonishing. Patches of the early cosmos lighting up like fireworks, with entire clusters of stars igniting in sudden, violent bursts. These weren't the faint, solitary beacons we imagined. They were cosmic supernovas of creation, rewriting the timeline of star formation in a single stroke. What's even more surprising is the scale. These stellar nurseries didn't just produce a handful of modest stars, they birthed giants, monsters hundreds of times more massive than our sun, burning furiously and dying young in spectacular explosions. Those explosions, in turn, seeded the universe with heavy elements far earlier than anyone predicted, scattering the building blocks of planets and life across the cosmos at breakneck speed. Suddenly, the story of galaxy formation isn't a gradual waltz. It's a mosh pit of chaos and energy, where entire galaxies could have taken shape in the blink of a cosmic eye. And here's where it gets really strange. If stars formed this explosively, their light should have ripped apart the delicate hydrogen fog filling the early universe, clearing the way for transparency much faster than our models suggested. That means the cosmic dawn might have been shorter, brighter, and far more turbulent than we ever dreamed. A revelation that forces us to rethink everything from the life cycle of galaxies to the very nature of dark matter's influence. Speaking of dark matter, its role in this explosive era might be even weirder than we thought. Dark matter was supposed to be the universe's quiet architect, an invisible hand gently shaping the cosmos without ever stepping into the spotlight. For decades, scientists assumed it simply hung in the background, its gravity slowly pulling gas and dust together to form the first stars and galaxies. But the latest simulations paint a radically different picture. Dark matter might have been anything but passive during the cosmic dawn. Instead, it could have been an active participant, even a provocateur, stirring up the early universe in ways we never anticipated. Imagine a cosmic dance where dark matter doesn't just lead, it accelerates. New data suggests it didn't merely provide a gravitational scaffold. It may have clumped together in dense, unpredictable knots, creating pockets of intense gravity that turbocharged star formation. These clusters could have acted like cosmic incubators, compressing gas so violently that entire galaxies burst into existence far sooner than our models predicted. Some simulations even show dark matter filaments, those vast, thread-like structures stretching across the universe, twisting and interacting in ways that funneled matter into galaxies at breakneck speed. This isn't just a tweak to the theory, it's a revolution. If dark matter was this dynamic, it challenges some of our most fundamental assumptions about its nature. Could it interact with itself in ways we haven't detected? Might there be hidden forces at play beyond gravity that shaped the early universe? The implications ripple outward, forcing us to reconsider everything from galaxy formation to the ultimate fate of the cosmos. And then there's the black hole connection. If dark matter was this active, its behavior could explain one of the biggest cosmic dawn mysteries: how supermassive black holes appeared so early in the universe's history. These gravitational monsters, weighing billions of times the mass of our Sun, shouldn't have had time to form in the universe's infancy unless something gave them a head start. Now, scientists wonder, did dark matter's chaotic influence create the perfect conditions for these behemoths to arise almost instantly? The answer might rewrite not just the story of the cosmic dawn, but the entire timeline of cosmic evolution. Supermassive black holes were supposed to be the universe's slowpokes, cosmic giants that took their sweet time growing, gobbling up matter over billions of years until they reached their staggering sizes. That's the story astronomers clung to for decades, but the universe, it seems, loves a plot twist. The James Webb Space Telescope has been peeling back the layers of time, and what it's found has left scientists reeling. Quasars, the blazing beacons powered by supermassive black holes, shining brightly in the universe's infancy. These monsters weren't just early, they were already fully grown when the cosmos was barely out of its diapers. So how did they get so big so fast? One possibility is that the first generation of stars didn't just die, they collapsed in ways we never saw coming. Imagine a star hundreds of times more massive than our Sun, burning furiously for just a few million years before imploding straight into a black hole, skipping the usual stellar death throes. These primordial titans could have served as instant seeds, jump-starting black hole growth at speeds that defy conventional physics. But there's an even wilder idea on the table. What if these black holes didn't form from stars at all? Some theorists now suggest they might have been born directly from the collapse of vast, dense gas clouds in the early universe, bypassing the star stage entirely. This isn't just a small adjustment to the timeline, it's a complete overhaul of galactic evolution. If supermassive black holes were already lurking in the cosmic dawn, they weren't just passive observers. Their intense gravity would have shaped their host galaxies from the very beginning, heating up surrounding gas, suppressing star formation, and even funneling matter into colossal jets that lit up the early cosmos. Suddenly, the story of galaxy formation isn't just about stars and gas. It's a tale of dark behemoths pulling the strings behind the scenes. And here's the real kicker. If black holes could form this quickly, it might mean our understanding of gravity itself is incomplete. Could exotic physics like primordial black holes left over from the Big Bang have given them a head start, or was there some unknown process in the early universe that turbocharged their growth? Every answer leads to more questions, and with each discovery, the cosmic dawn looks less like a gentle sunrise and more like a cosmic roller coaster. Which brings us to the next shattered assumption, one that might rewrite the story of the very first stars. The first stars weren't the lonely titans we pictured, solitary giants burning in the void, their light the only break in an endless darkness. For years, that was the dominant image, massive, short-lived behemoths, hundreds of times heavier than our sun, blazing alone before vanishing in spectacular supernovas. But the universe, as usual, had other plans. Recent observations suggest these pioneers weren't solo acts at all. Instead, they may have been born in bustling stellar nurseries, crowded with siblings smaller, more numerous stars than anyone predicted. This discovery flips the script on early cosmic history. If the first stars formed in clusters, their combined light would have been far brighter and more widespread than we imagined, punching holes in the hydrogen fog of the early universe much faster. But the real game changer is what this means for the ingredients of life. Those early stars didn't just live and die, they cooked the universe's first heavy elements in their cores, then scattered them in violent explosions. With more stars forming together, that process wasn't just happening in isolated bursts. It was a cosmic assembly line, churning out carbon, oxygen, and iron at a rate that could have seeded the cosmos with life's building blocks far earlier than we thought. Here's where it gets even wilder. If these stars were smaller and more numerous, they might have lived longer. Some could even still exist today, lurking in the outskirts of our galaxy like living fossils from the cosmic dawn. The idea that we might one day spot a star from the universe's first generation, a relic older than the Milky Way itself, is enough to send shivers down any astronomer's spine. And then there's the light. If star clusters were common, the early universe wasn't the pitch-black wilderness we envisioned. Instead, it might have been dotted with glowing archipelagos, patches of brilliance where these stellar families blazed together. That changes everything about how we model the era when light first conquered the cosmos, because darkness, it seems, never stood a chance. Which brings us to the next shattered assumption. The cosmic dawn wasn't just a slow unveiling. It was a revolution, a firestorm of light rewriting the rules from the very beginning. The cosmic dawn was never supposed to be this uneven. For years, textbooks described it as a vast, uniform shroud of darkness, a cosmic curtain slowly lifting as the first starlight crept in. But the universe, it turns out, has a flair for the dramatic. Radio telescopes scanning the depths of time have picked up something extraordinary. Patches of the early cosmos glowing with unexpected brightness, like scattered bonfires in an endless night. These anomalies don't just tweak the story, they tear it apart. What could have caused these bright islands in the darkness? One possibility is that early galaxies weren't spread evenly like butter on toast. Instead, they might have clustered in dense, blazing metropolises, leaving vast deserts of emptiness between them. Imagine walking through a forest where trees grow in tight, towering groves but vanish completely just a few steps away. That's the kind of patchwork universe we're talking about, a place where light didn't diffuse gently but erupted in sudden, dazzling bursts. But here's where it gets stranger. Some of these bright spots don't match the expected signature of starlight at all. They hint at something even more exotic, radiation from unknown sources, possibly even the fingerprints of dark matter itself. Could decaying particles or collapsing primordial black holes have lit up pockets of the early universe? The data isn't just surprising, It's forcing scientists to rewrite the playbook on how light first conquered the cosmos. And then there's the timing. These bright patches appear too early, too abruptly, as if the universe flicked on a switch in some places while leaving others in shadow. That challenges the very idea of a smooth, gradual transition to transparency. Instead, the cosmic dawn might have been a chaotic mosaic, with light punching through in erratic surges, like cracks in ice spreading unpredictably. What does this mean for our understanding of the early universe? For starters, it suggests that the first galaxies didn't just form, they exploded onto the scene, reshaping their surroundings with incredible speed. And if light wasn't evenly distributed, neither was heat. That uneven heating could have triggered wild variations in gas density, accelerating star formation in some regions while stifling it in others. Suddenly, the story of cosmic evolution isn't just about time, it's about place, which brings us to the next revelation. The cosmic dawn wasn't just uneven. It was alive with structures we're only beginning to recognize, structures that might rewrite the rules of galaxy formation itself. Reionization was never supposed to be this messy. For decades, astronomers envisioned it as a single, triumphant wave, a cosmic tide of light sweeping across the universe, burning away the fog of hydrogen gas in one clean, decisive motion. But the universe doesn't do tidy. The latest observations reveal a process far more chaotic, with some regions blazing into clarity eons before others, as if the cosmos couldn't decide whether to flip the lights on or off. This isn't just a minor wrinkle in the story, it's a fundamental rewrite of how we think about the universe's transformation from darkness to light. Take a closer look at those early galaxies, and the plot thickens. Some of them appear to have ionized their surroundings shockingly early, like overachievers turning in homework before the bell even rings. Their radiation was so intense it punched holes in the hydrogen fog around them, creating isolated bubbles of clarity in an otherwise murky cosmos. Meanwhile, other regions lagged behind, stubbornly clinging to their primordial haze for hundreds of millions of years longer. This patchwork reionization throws a wrench into every existing model because it means the universe didn't have one clear turning point. It had hundreds, maybe thousands, scattered across space and time like a broken string of holiday lights. What could have caused this unevenness? The usual suspect stars and quasars don't quite add up. Their combined light should have created a more uniform wave, not this haphazard flickering. That leaves us with a thrilling possibility. Something else was out there, something powerful and unpredictable, helping to strip electrons from hydrogen atoms in fits and starts. Maybe it was an early population of supermassive black holes, feasting on gas and belching out radiation in erratic bursts. Or perhaps dark matter played a role, its hidden interactions triggering localized surges of energy. Whatever the cause, one thing's clear: the universe's great unveiling was anything but orderly. And here's where it gets even stranger. If reionization happened in patches, it means the cosmic dawn was more like a strobe light flashing on and off in different places at different times, with no grand conductor keeping the rhythm. That uneven lighting would have created wild variations in temperature and pressure, sculpting the gas between galaxies into a lumpy, unpredictable landscape. Some regions might have cooled just enough to collapse into new stars, while others stayed hot and diffuse, starving future galaxies of their building blocks. Suddenly, the story of cosmic evolution isn't just about when galaxies formed, it's about where and why some neighborhoods got a head start while others were left in the dark. Which brings us to the next revelation. Early galaxies weren't just bystanders in this chaos. They were the Arsonists, setting the cosmos ablaze in ways we're only beginning to understand. Early galaxies weren't supposed to have rules. Conventional wisdom painted them as cosmic wildlings, chaotic, turbulent places where gas swirled in violent, disordered storms, too unstable to settle into anything resembling structure. The early universe was a demolition derby, not a ballet, or so we thought. When the James Webb Space Telescope turned its golden eye toward these primordial giants, it didn't find the messy free-for-all we expected. Instead, it captured something that sent shockwaves through astronomy. Galaxies with delicate spiral arms, elegant disks, and even barred structures, features so refined they looked like they'd been plucked from the modern cosmos and thrown billions of years into the past. This wasn't just unexpected, it was borderline heresy. How could galaxies, barely a few 100 million years old, already exhibit such poise? The prevailing theory said it should take eons for gravity to sculpt gas into orderly shapes, with countless collisions and mergers gradually smoothing out the chaos. Yet here were these ancient galaxies flaunting their symmetry like cosmic overachievers. The implications are staggering. If disks and spirals formed this early, the young universe wasn't just a riot of collisions. It had pockets of startling calm, places where gas settled into stable orbits almost instantly. So what forced the chaos into order so quickly? One tantalizing clue lies in dark matter. The invisible scaffolding of the cosmos might have played a far more active role than we realized. Imagine dark matter halos, those vast, ghostly cocoons surrounding galaxies acting like cosmic stabilizers. If they were unusually dense or rigid in the early universe, their gravity could have corralled gas into disks before turbulence had a chance to take hold. It's like stirring cream into coffee and watching it instantly form perfect swirls instead of chaotic eddies. Something unseen is guiding the motion. But there's another, even more radical possibility. What if early galaxies weren't born from slow accumulation, but from rapid, monolithic collapses? Picture a massive gas cloud, pristine and cold, collapsing in one smooth motion, no messy mergers, no violent collisions, just a single, graceful descent into a spinning disk. This top-down formation would bypass the traditional growing pains of galaxy evolution, handing the universe ready-made spirals right out of the gate. And here's where the plot twists again. If galaxies stabilized this quickly, their stars would have formed in orderly orbits, not the scattered frenzy we assumed. That means the first generations of stars might have had longer, quieter lives, burning steadily in stable neighborhoods instead of being hurled into chaos by galactic turbulence. Suddenly, the early universe looks less like a mosh pit and more like a symphony, with dark matter as its unseen conductor, which brings us to the next revelation. If galaxies were this organized, their black holes might have been too, and that changes everything about how we think cosmic giants were born. Early galaxies weren't just inefficient, they were cosmic overachievers. For years, astronomers assumed these ancient star factories operated at a sluggish pace, struggling to gather enough gas to ignite new stars in the sparse early universe. The math seemed simple. Fewer raw materials should mean slower production. But when scientists pointed telescopes at these infant galaxies, they found something astonishing: stellar assembly lines running at full tilt, churning out stars at rates that would put even the Milky Way to shame. These weren't the cosmic backwaters we imagined. They were blazing metropolises of creation, defying every expectation about how star formation works. So how did they do it? One clue lies in the gas itself. Modern galaxies rely on recycled material, dusty, metal-rich clouds left behind by dead stars. But the early universe was pristine, filled with pure hydrogen and helium, free from the pollution of heavier elements. Counterintuitively, this might have been their secret weapon. Without metals to cool the gas efficiently, It could have collapsed into stars more violently, like a thunderstorm with nothing to slow the downpour. Picture a cloud of gas so cold and dense it fractures into stars almost instantly, with none of the hesitation we see in today's galaxies. But there's another twist: the fuel delivery system. Some theorists suggest these early galaxies weren't just passively collecting gas, they were hooked up to cosmic pipelines, vast streams of cold gas flowing in from the cosmic web. These rivers of raw material could have fed star formation continuously, like a conveyor belt feeding a furnace, and here's where dark matter might have played puppeteer. If dark matter halos were more tightly wound in the early universe, their gravity could have funneled gas into galaxies with terrifying efficiency, compressing it into stars before it had a chance to escape. The implications are staggering. If star formation was this efficient, it means the first galaxies could have reached maturity in a cosmic blink, their light flooding the universe far sooner than anyone predicted. And that changes everything about how we model the reionization era, the moment when starlight burned away the cosmic fog. With stars forming this fast, the universe might have gone from darkness to light in a frenzied rush, not the slow dawn we've been picturing. Now let's talk about the aftermath. All those stars didn't just live and die quietly, they cooked up something revolutionary in their cores, the universe's first heavy elements. Conventional wisdom says these ingredients should have been scarce in the early cosmos, sprinkled like rare spices across a vast, bland soup. But what if we've underestimated the chefs? With star formation running at warp speed, the kitchen might have been far busier and the menu far richer than we ever dreamed. Heavy elements weren't supposed to be this old. The early universe was meant to be pristine, a blank canvas of hydrogen and helium, untouched by the forge of stars. But light from ancient quasars tells a different story. Their spectra, captured by telescopes like the James Webb, reveal something astonishing: fingerprints of carbon and oxygen etched into gas clouds so ancient they predate most galaxies. These aren't just trace amounts either. Some clouds contain heavy elements at levels that defy every simulation, as if the first stars didn't just sprinkle metals into the cosmos, they dumped them by the bucketful. What does this mean for the timeline of everything? If stars were churning out carbon and oxygen this early, the universe's chemical kitchen was open for business far sooner than we imagined. And that changes the game for planet formation. Heavy elements are the building blocks of rocky worlds: the silicon for continents, the iron for cores, the oxygen for water. If they were abundant in the cosmic dawn, the first habitable planets might have formed when the universe was just a fraction of its current age. Imagine Earth like worlds orbiting stars born barely a few 100 million years after the Big Bang, their surfaces cooled and ready for oceans while the cosmos was still in its infancy. But here's the real mind bender. If planets existed that early, could life have arisen too? The conventional answer was a firm no. The universe needed billions of years of stellar recycling to cook enough ingredients for biology. But these quasar spectra throw that assumption into doubt. Carbon, oxygen, even nitrogen, these are the raw materials of DNA, the scaffolding of proteins. If they were available so soon, the clock for life's potential might start ticking much earlier. Of course, habitability isn't just about ingredients. Early planets would have faced brutal conditions, intense radiation, frequent supernova, and gravitational chaos as galaxies clashed. But life as we know it is stubborn. Single-celled organisms on Earth thrive in boiling vents, acidic pools, and even the crushing depths of ice. If extremophiles can hack it here, why not on an ancient world bathed in the glow of the first stars? And then there's the wild card. What if the first stars weren't the only polluters? Some theories suggest that exotic processes like colliding neutron stars or evaporating primordial black holes could have peppered the early universe with heavy elements even before stars dominated. If true, the cosmic dawn might have been a gold rush of cosmic chemistry, with metals appearing in places and quantities we've barely begun to imagine. One thing's clear, the universe didn't waste time getting interesting. The old story of a slow, patient build toward complexity is crumbling. Instead, we're seeing a cosmos that hit the ground running, transforming itself from simplicity to richness in a dizzying sprint. And if life had a head start, that raises a thrilling question. What else was possible in those forgotten eons when the first starlight was still new? The early universe was supposed to be a death zone, a radioactive wasteland where no living thing could survive. With massive stars exploding like cosmic grenades and ultraviolet radiation scorching every corner of space, the idea that life might have found a foothold during the cosmic dawn seemed laughable. Until now, cutting-edge simulations are revealing something extraordinary. Shielded pockets where life could have not only survived but possibly even thrived. Imagine vast molecular clouds, dense as velvet curtains, absorbing the worst of the radiation while creating sheltered oases within. Inside these cosmic bunkers, temperatures might have been just right for liquid water to pool on rocky worlds, while the chaos outside raged on unseen. What's truly wild is the scale of these safe havens. Some models suggest entire proto-galaxies could have acted like radiation shields, their thick halos of gas and dust deflecting or absorbing deadly energy. Picture a planet orbiting a small, quiet star tucked deep within one of these protective bubbles, a world where the sky glows faintly with distant starlight, but the surface remains untouched by the inferno beyond. Even more surprising, these sheltered zones might have been more common than we thought. While massive stars dominated the early cosmos, they weren't evenly distributed. Vast regions of space could have existed in relative calm, far from the nearest supernova, where conditions were stable enough for chemistry to begin its delicate dance toward complexity. But here's the twist. If life had a chance this early, it changes everything about how we search for its origins. Instead of assuming biology needed billions of years of cosmic evolution to get started, we might need to consider that life could have arisen, died out, and risen again multiple times over the universe's history. Some of the oldest planets, those forged in the fires of the cosmic dawn, might have been the first to crack the code of existence, only to vanish beneath the ashes of time. And then there's the radiation itself. New calculations show it wasn't just a destructive force, it might have been a catalyst. High-energy particles slamming into primordial atmospheres could have sparked chemical reactions that built the precursors to life, like a cosmic forge hammering raw elements into something new. The same radiation that seemed lethal might have been the spark that lit the fuse, which brings us to the next revelation. The early universe wasn't just a violent void. It was a place of paradoxes where destruction and creation danced together, and in the shadows between them, life might have found a way. The early universe was supposed to be a silent movie, a vast, still expanse where the first stars and galaxies formed in near-perfect quiet, their birth pangs muffled by the emptiness of space. But what if we've been listening to the wrong channel? Gravitational wave detectors, those ultra-sensitive ears tuned to the vibrations of spacetime itself, are picking up whispers of something extraordinary, echoes of colossal collisions from the cosmic dawn, ripples of violence that suggest the universe's infancy was anything but peaceful. Imagine the shockwaves from black holes the size of solar systems slamming together, or cosmic strings. Those hypothetical flaws in spacetime's fabric snapping like guitar strings with enough force to shake the cosmos. These aren't just theoretical curiosities, they're potential fingerprints of a universe that roared to life in a frenzy of chaos. the implications are staggering. If gravitational waves from this era are detectable, it means the early universe wasn't just lively, it was a demolition derby of unimaginable scale. Primordial black holes, those hypothetical leftovers from the Big Bang, might have been the main players. Picture swarms of these ancient monsters, some as massive as stars, others as small as asteroids, crashing into one another in the darkness long before the first stars flickered on. Each collision would have sent gravitational tsunamis rippling across spacetime, a cacophony we're only now tuning into. Even wilder, these black holes might not have formed from dying stars at all. They could be relics of the universe's birth, bubbles of ultra-dense matter that collapsed directly into singularity in the first fractions of a second after the Big Bang. But black holes aren't the only suspects. Cosmic strings, if they exist, could have turned the early universe into a cosmic drumhead. These bizarre one-dimensional defects in space-time, thinner than an atom but stretching across the cosmos, would have vibrated as the universe expanded, possibly creating gravitational waves powerful enough to survive billions of years. Think of plucking a rubber band stretched across a room, except the rubber band is a crack in reality, and the pluck is a shock wave that bends the fabric of existence. If detectors like LIGO or future space-based observatories catch these echoes, it wouldn't just rewrite the story of the cosmic dawn. It would force us to rethink the very nature of spacetime. And here's the twist: these gravitational waves aren't just noise, they're a time machine. Every ripple carries information about the era it came from, the temperature of the universe, the density of matter, even the shape of hidden dimensions. By decoding them, we could glimpse the cosmic dawn in a way light alone can't show us. Light gets absorbed, scattered, or obscured by gas and dust, but gravitational waves pass through everything untouched, like ghosts walking through walls. They could reveal a chapter of cosmic history that's been invisible until now, which brings us to the next revelation, one that challenges not just what happened in the early universe, but when it happened. Because time itself might not have flowed the way we think it did. Time might not have ticked the same way during the cosmic dawn as it does today, and that changes everything about how we measure the universe's earliest moments. Einstein's theory of relativity tells us gravity doesn't just bend space, it warps time itself. Near a black hole, seconds stretch like taffy. In the early universe, where matter was packed unimaginably dense, time could have flowed slower by a factor of hundreds or even thousands. Picture a cosmic hourglass where the sand pours sluggishly in those first turbulent eras, then speeds up as the universe expands and thins out. This isn't just theoretical poetry, it's a potential bombshell for how we interpret the cosmic dawn's timeline. Take those impossibly early supermassive black holes we've detected. If time near them crawled relative to the rest of the universe, what looks like rapid growth to us might have unfolded over far longer periods from their perspective. A black hole that appears to reach billion solar mass sizes in just a few 100 million years. From its own reference frame, it could have had billions of years to feast on gas, plenty of time to grow to monstrous proportions. Suddenly, the impossible timing isn't impossible at all. We've just been reading the cosmic clock wrong, but here's where it gets even stranger. This time dilation wouldn't have been uniform. Regions with denser matter, like the cores of early galaxies, experienced more severe slowing than the emptier voids between them. The result, a universe where time fractured into countless local rhythms, like a symphony where every instrument plays at a different tempo. A star forming in one pocket of space might have lived and died before another star, born simultaneously but in a less dense region, even finished collapsing. This patchwork timeline turns the cosmic dawn into a surreal collage of events that may not have been as simultaneous as we assumed. And then there's the light. When we observe distant galaxies, we're not just looking across space, we're peering back through layers of warped time. Their light, emitted in a slower ticking epoch, reaches us stretched and reddened, carrying echoes of that primordial time dilation. But what if we've been misinterpreting those signals? The redshift we use to measure cosmic distances assumes time flowed uniformly. If it didn't, some galaxies might be closer or older than we've calculated, throwing our maps of the early universe into disarray. This revelation doesn't just tweak the cosmic dawn's timeline, it forces us to rethink the very definition of early. Events we thought happened in sequence might have overlapped. Processes we believed were instantaneous could have dragged on for eons in their own reference frames. Even the universe's age, currently pegged at 13.8 billion years, might need recalibrating if vast stretches of its infancy passed in extreme slow motion. Which brings us to the next enigma. If time was this elastic, why haven't we found more traces of the universe's tiniest galaxies? According to theory, the cosmic dawn should have spawned countless dwarf galaxies, small, faint companions to the larger ones we've spotted. But where are they? The answer might lie in how time's uneven flow shaped their fate. Dwarf galaxies should have been everywhere in the cosmic dawn, tiny, faint smudges of stars dotting the universe like fireflies in a dark field. Computer simulations painted a clear picture. Dark matter's gravity should have sculpted countless miniature galaxies, each a fraction the size of the Milky Way, swarming around their larger siblings like cosmic minnows. But when astronomers finally trained their telescopes on the early universe, they found a ghost town, where simulations predicted thousands, observations revealed only a handful. This glaring mismatch isn't just a minor discrepancy, it's a full-blown crisis for our understanding of dark matter and galaxy formation. So where did all the dwarfs go? One possibility is brutal. The early universe might have been a galactic slaughterhouse. Intense ultraviolet radiation from massive stars could have sterilized smaller galaxies, stripping away their gas before they had a chance to form many stars. Picture a cosmic hurricane scouring tiny islands clean, leaving behind barren husks too faint to detect. Another theory suggests these dwarfs were there, but merged so quickly they vanished before we could spot them, swallowed by larger galaxies in a feeding frenzy of collisions. But the most unsettling idea, the simulations might be fundamentally wrong. The missing dwarfs could be a smoking gun that dark matter doesn't behave the way we think. Most models assume dark matter is cold, slow-moving and clumpy, perfect for building small-scale structures like dwarf galaxies. If it's instead warm, with particles zipping around too fast to form tiny clumps, that could explain their absence. Or perhaps dark matter interacts with itself in ways we haven't imagined, smoothing out the small-scale ripples that would have birthed these galaxies. Now flip the problem on its head. While some galaxies are mysteriously missing, others are bafflingly bright. The cosmic dawn wasn't just about the vanishing dwarfs, it also hosted galaxies shining with impossible brilliance, their light-defying expectations. These overachievers radiate more energy than their size suggests they should, as if someone cranked the universe's brightness dial to 11. What's powering these cosmic lighthouses? One clue lies in their star formation rates, which are off the charts. While modern galaxies like the Milky Way birth maybe 1 or 2 stars a year, these ancient giants could have churned out hundreds, their stellar factories running at full throttle. But here's the catch, they shouldn't have had enough fuel. Star formation requires cold gas, and the early universe was supposed to be too hot for large reservoirs to exist. Unless, of course, our assumptions about gas cooling are wrong. Enter supermassive black holes again. Their ferocious energy output might have created a paradox. While they heated surrounding gas, their jets could have also carved out cavities where gas cooled rapidly, like frost forming in the wake of a blowtorch. These cold pockets might then have collapsed into waves of new stars, creating a feedback loop of brilliance. Or perhaps dark matter's hidden physics played a role, its gravitational tinkering funneling gas into galaxies with freakish efficiency. The real shocker, some of these bright galaxies appear to be isolated, floating in voids rather than clustered with others. That flies in the face of everything we know about galaxy formation, which relies on dense environments to trigger such extreme activity. It's like finding a bustling metropolis in the middle of a desert, a cosmic head-scratcher that forces us to rethink how structure emerges in the universe. Taken together, the missing dwarfs and the two bright giants paint a picture of a cosmic dawn far more complex than we ever imagined. The universe wasn't just assembling galaxies, it was playing by rules we're only beginning to decipher. And with every new observation, the mystery deepens, hinting at physics beyond our current grasp, which raises the next question. If the rules were different back then, what else don't we know about how the cosmos grew up? Some of the earliest galaxies shouldn't just glow, they should blaze like cosmic supernovas, defying every rule we thought we knew about luminosity. When astronomers first spotted these radiant anomalies in deep field images, the numbers didn't add up. Their light output was off the charts, shining with the intensity of modern galaxies hundreds of times their size. It's like finding a candle that burns as bright as a stadium floodlight. Something fundamental about our understanding of starlight is missing. Theories rushed in to explain the impossible. Maybe these galaxies hosted stars unlike anything we've seen, monstrous, ultra-efficient furnaces that converted fuel into light at near-perfect efficiency. Picture a star so potent it could outshine our sun by a factor of millions, burning pure hydrogen with none of the waste heat that slows down modern stars. These hypothetical supermassive population 3 stars could have been the universe's first overachievers, their brilliance rewriting the limits of stellar physics. But there's a catch: we've never actually seen one. They should have left behind chemical fingerprints in ancient gas clouds, yet the evidence remains elusive. Then there's the black hole factor. Some of these radiant galaxies might not be lit by stars at all. Their light could be the death screams of matter spiraling into supermassive black holes, quasars on steroids, pumping out energy as entire suns are shredded into plasma. But even that explanation hits a wall. Quasars need time to grow, and these galaxies shine too early, too brightly, as if the black holes inside them were born already feasting. The real answer might lie in a cosmic loophole we never saw coming. Dark matter, often the universe's silent partner, could have played puppeteer. If certain forms of dark matter particles decayed or collided, they might have injected energy directly into these early galaxies, supercharging their glow like invisible power plants. Or perhaps the fabric of space itself was different, a universe so dense that nuclear reactions in stars ran hotter and faster, like a pressure cooker cranking starlight to extremes. Whatever the cause, one thing's clear: the early cosmos didn't just flicker to life. It erupted in flares of brilliance we're only beginning to decode. And if light itself bent the rules back then, what other cosmic laws were written in pencil, not stone? The next shattered assumption might hold the key, because when it comes to the cosmic dawn, even the brightest answers cast deeper shadows. We always imagined the early universe as a uniform oven, heating up steadily as the first stars flickered on. A predictable, gradual rise in temperature, like turning up a dial. But the cosmic dawn refused to follow the script. Astronomers mapping the ancient cosmos have stumbled onto a bizarre patchwork of hot and cold regions. as if someone left a cosmic air conditioner running in some corners while others baked under invisible heat lamps. This isn't just a minor irregularity, it's a full-blown thermodynamic rebellion, one that could rewrite our understanding of how energy flowed in the universe's infancy. Take the case of two gas clouds, both dating back to just a few 100 million years after the Big Bang. One blazes with the heat of 1,000 stars, its atoms buzzing with energy. The other sits eerily cool, barely warmer than the cosmic microwave background. They should be identical twins, born from the same primordial soup, yet somehow they're living in entirely different climates. The difference isn't just puzzling, it's physically implausible under conventional models. Heat should have spread evenly, smoothing out these variations long before the cosmic dawn began. The fact that it didn't suggest something or someone was tinkering with the thermostat, one leading suspect, the first black holes. These gravitational monsters could have pumped out torrents of X-rays, heating surrounding gas to blistering temperatures in isolated pockets. But here's the catch, their reach should have been limited. No known black hole can explain the vast, continent-sized hot zones we're seeing. Unless, of course, early black holes were far more numerous or energetic than we've calculated. Or perhaps dark matter played a role, its mysterious interactions releasing bursts of heat in random eruptions. Some theorists even speculate that dark energy, the force accelerating the universe's expansion today, might have left fingerprints in this uneven heating, a clue that its influence began much earlier than we thought. Then there's the cold spots. These cosmic frost pockets defy explanation even more stubbornly. In a universe still glowing from the Big Bang's residual heat, how did some regions stay so chilly? One radical idea points to cosmic strings, hypothetical defects in spacetime's fabric acting like refrigerators. As these strings vibrated, they might have created expanding bubbles of cooler space, like ice crystals forming in supercooled water. Or maybe the cold zones are shadows cast by primordial black holes, their gravity bending radiation away from certain areas, leaving behind patches of unexpected coolness. The implications ripple far beyond temperature maps. If heat wasn't distributed evenly, neither was the pressure that shaped galaxy formation. Hot regions would have pushed gas outward, stifling star birth, while cold zones let gas collapse into stellar nurseries with freakish efficiency. This uneven playing field could explain why some galaxies matured shockingly fast while others lagged behind. A galactic haves and have-nots divide baked into the cosmos from the very beginning. And here's the real kicker, this thermal patchwork might still be with us today. The cosmic microwave background, the afterglow of the Big Bang, shows faint temperature variations that could be echoes of this ancient imbalance. If so, we're not just studying the cosmic dawn's weather report, we're reading a message left behind in the universe's very first heat waves, a code that might reveal secrets about dark energy, dark matter, and forces we've yet to name. Which brings us to the next cosmic curveball, galaxies that look far too grown up for their age. If the universe's temperature was this chaotic, its maturation process might have been too, and the evidence is written in starlight, older than it should be. Galaxies weren't supposed to have midlife crises, at least, not when the universe was barely a toddler. Conventional wisdom said these cosmic islands needed billions of years to settle into their mature forms, their spiral arms and bulging centers slowly sculpted by gravity's patient hands. But the James Webb Space Telescope just caught a group of ancient galaxies red-handed, flaunting sophisticated structures and elderly stars when, by all rights, they should have been cosmic infants. It's like finding a preschooler who's already retired, a violation of nature's timeline so glaring it threatens to upend our entire understanding of galactic evolution. Let's break down the crime scene. one of these galaxies, spotted when the universe was just 5% of its current age, sports a well-defined disk and central bulge, features that typically take eons to develop. Worse, its stars are old, not just a little weathered but genuinely ancient, suggesting they formed shockingly early and fast, like a cosmic speedrun of stellar aging. How could this be? One radical theory suggests these galaxies didn't grow gradually at all. Instead, they might have collapsed all at once from enormous, dense clouds of gas, skipping the usual growing pains of mergers and collisions. Picture a ball of dough flattening into a perfect pizza in one swift motion, no kneading required. But here's where the plot twists. If galaxies matured this quickly, it implies the early universe was far richer in raw materials than we thought. There had to be enough cold, dense gas lying around to fuel rapid star formation, a cosmic buffet where these galaxies gorged themselves to maturity. That contradicts our models of the cosmic dawn, which paint a sparser, hotter environment where gas should have been too diffused to collapse so efficiently. Unless, of course, dark matter's hidden scaffolding was more intricate than we realized, funneling gas into these galaxies with terrifying precision. And then there's the lithium problem. While astronomers grapple with these inexplicably grown-up galaxies, chemists are staring down their own cosmic anomaly, the universe's missing lithium. According to Big Bang nucleosynthesis, the recipe that cooked up the first elements, there should be about 3 times more lithium in the cosmos than we've actually found. It's like baking a cake and discovering half the sugar vanished before the oven even preheated. Where did it go? Some theories suggest primordial black holes devoured it, or that exotic particles interacted with lithium nuclei, breaking them apart. Others propose that early stars processed lithium far more efficiently than we thought, burning it up like kindling in their cores. But the wildest idea: the laws of nuclear physics might have operated slightly differently in the universe's first moments, tweaking the elemental ratios in ways we're only now detecting. Connect the dots and a startling pattern emerges. If galaxies matured faster than expected and lithium mysteriously vanished, maybe both puzzles share a common thread, a hidden variable in the early universe's physics that accelerated some processes while suppressing others. It's as if the cosmos had a set of cheat codes bending the rules to fast-track complexity. The question now isn't just how these anomalies happened, it's what other shortcuts the universe might have taken to become the rich, structured place we see today. Big Bang nucleosynthesis was supposed to be a perfect cosmic recipe, a precise mathematical equation that cooked up the first elements in exact, predictable quantities. Hydrogen and helium, check. A dash of lithium. According to the calculations, there should be about 1 lithium atom for every 10 billion hydrogen atoms scattered across the cosmos. But when astronomers went hunting for this primordial lithium, they came up shockingly short. The universe's pantry is missing nearly 2/3 of its expected lithium supply, and no one knows where it went. This isn't just a rounding error, it's a gaping hole in our understanding of the universe's first moments, one that hints at physics beyond the standard model. So where did the lithium vanish? One tantalizing possibility involves hypothetical particles called actions, ghostly entities predicted by some theories of dark matter. These could have interacted with lithium nuclei in the early universe, breaking them apart before stars had a chance to form. Picture a cosmic game of pool where invisible cue balls scattered the lithium, leaving us with only fragments of the original stash. Another theory points to primordial black holes, those ancient gravitational traps swallowing lithium-rich gas before it could settle into stars. Or perhaps the lithium never vanished at all. Maybe it's hiding in plain sight, locked inside brown dwarfs or drifting between galaxies in forms we haven't yet detected. But here's where it gets really wild. The lithium discrepancy might not be about missing matter at all. It could be a sign that the laws of nuclear physics operated differently under the extreme conditions of the early universe. The energies and densities during Big Bang nucleosynthesis were unlike anything we can replicate in labs today. What if nuclear reactions ran slightly faster or slower back then, tweaking the final elemental mix? It's like baking a cake at sea level versus the top of Mount Everest. The same recipe can yield startlingly different results. Now, shift gears to another cosmic surprise: primordial galaxies spinning faster than physics allows. When astronomers measured the rotation speeds of some of the universe's oldest galaxies, they found something impossible: disks whirling so rapidly they should have torn themselves apart. According to our models, these ancient galaxies simply didn't have enough mass to hold together at such speeds. Yet there they are, defying gravity's grip like cosmic daredevils. The culprit: dark matter again, but not as we know it. These galaxies might be embedded in dense, invisible halos that extend far beyond their visible edges, providing the extra gravitational glue needed to keep them intact. Or perhaps dark matter interacts with itself in ways we haven't accounted for, creating unexpected torque that spins galaxies up like tops. There's even a fringe idea that the early universe's higher density altered the effective strength of gravity on galactic scales, a tweak that would rewrite the rules of cosmic mechanics. Connect these two mysteries, the missing lithium and the hyper-spinning galaxies, and a pattern emerges. The early universe wasn't just a scaled-down version of today's cosmos. It operated under a subtly different set of rules, with particles, forces, and dynamics we're only beginning to glimpse. Every anomaly is a breadcrumb leading us deeper into the labyrinth of cosmic origins, where the next shattered assumption might reveal not just how the universe works, but why it works the way it does. And speaking of assumptions, wait until you hear about the galaxies that appear to be older than the universe itself. Early galaxies weren't supposed to spin like cosmic tops, especially not faster than their modern descendants. Conventional wisdom said rotation should build gradually, with galaxies gaining momentum as they grew through mergers and accumulated mass. But the universe, it seems, loves a paradox. Observations of some primordial galaxies revealed disks whirling at breakneck speeds, their outer stars hurtling so fast they should have been flung into the void like riders ejected from a runaway carousel. This isn't just a minor discrepancy, it's a full-blown revolt against the laws of angular momentum, forcing us to rethink how the first galaxies got their groove. So how did these ancient whirlpools defy physics? One clue lies in their birth environment. The early universe was a far more turbulent place than today's cosmos, filled with supersonic gas flows and violent mergers. Picture a galaxy forming not in a quiet pond, but in the heart of a hurricane, where chaotic currents could have imparted insane rotation from the very beginning. Magnetic fields might have amplified the effect, acting like cosmic twirlers' batons, spinning gas clouds into dizzying vortices before they even collapsed into stars. But the real game changer: dark matter's hidden choreography. Simulations suggest dark matter halos in the early universe could have been threaded with swirling currents, vast, invisible whirlpools that dragged normal matter along for the ride. These dark vortices would have funneled gas into galaxies already pre-spun, like water spiraling down a drain. And here's the kicker: if dark matter was warm or self-interacting, as some theories propose, these currents could have been even more pronounced, turning primordial galaxies into cosmic figure skaters pulling off impossible spins. The implications ripple outward. If early galaxies rotated this fast, their shapes would have been radically different, flattened into razor-thin disks with towering shock waves at their edges. Star formation might have concentrated in frantic, spiral arm fireworks, scattering heavy elements in frenetic whirls rather than gentle sprinkles. Even black hole growth could have been supercharged, with infalling gas corkscrewing into the center at unprecedented rates. Now brace for the next curveball. If rotation defied expectations, wait until you hear how the universe's expansion, the very fabric of space-time, might have played by different rules in its youth. The universe's expansion wasn't supposed to stutter. For over a century, astronomers envisioned it as a smooth, relentless glide, a balloon inflating with perfect symmetry, carrying galaxies along for the ride. But the cosmos has a habit of breaking its own rules. Recent measurements of the Hubble constant, the rate at which the universe expands, reveal something startling: tiny fluctuations like cosmic hiccups, suggesting the early universe didn't balloon outward in one steady breath. Instead, it lurched forward in fits and starts, as if something were tugging at the fabric of space-time from the shadows. What could have caused these jerks in cosmic history? One provocative idea points to dark energy, not as the steady force we observe today, but as a capricious player in the universe's infancy. Imagine dark energy flickering on and off like a faulty light switch, alternately accelerating and breaking expansion in erratic bursts. Or perhaps it wasn't dark energy at all. Hidden dimensions predicted by string theory might have briefly warped space-time, creating expansion's uneven rhythm. Even more radical, the universe's constants weren't constant. The strength of gravity or the mass of fundamental particles could have shifted subtly in those first moments, rewriting the rules of cosmic growth on the fly. Now zoom out to the universe's texture. If expansion wasn't smooth, neither was its structure. The cosmic web, that vast network of galaxies and voids, should have formed from nearly imperceptible ripples in the primordial soup. But the deeper we look, the more lumpy it appears. Some regions are crammed with galaxies, others eerily empty, with disparities too stark to explain by random chance. It's as if the universe rolled cosmic dice and kept landing on extremes. The culprit might lie in quantum fluctuations, those microscopic tremors in spacetime's fabric during the Big Bang. Normally, they'd average out into a gentle cosmic hum. But what if some regions amplified these fluctuations, like echoes in a hall of mirrors? Dark matter's gravitational pull could have acted as an accomplice, sculpting overdense patches into galactic megacities while leaving deserts of emptiness between them. Or perhaps the universe's lumpiness is a fossil, a relic of exotic phase transitions in the first trillionth of a second, when space-time itself crystallized like ice, forming in uneven patches. Here's the twist: this lumpiness isn't just a curiosity. It's the reason we exist. Without those dense pockets, matter would have scattered too thinly for galaxies or life to ever form. The universe's imperfections, it turns out, were its greatest creative force, but the mystery remains. Why did it clump so unevenly? The answer might rewrite not just cosmic history, but our understanding of the forces that shaped it. And speaking of forces, there's another anomaly lurking in the data, one that suggests the early universe didn't just expand unevenly, it might have done so while spinning. The early universe was supposed to be a smooth, homogeneous soup, a perfectly stirred cosmic broth where matter spread evenly like butter on toast. But when astronomers mapped the large-scale structure of the cosmos, they found anything but order. Instead of a gentle gradient, the universe resembles a lumpy sponge, with vast voids stretching billions of light years alongside dense filaments of galaxies clumped together in chaotic webs. These structures didn't form slowly over eons, they emerged shockingly early, defying every simulation that predicted a more gradual buildup. It's as if the universe skipped the simmering phase and went straight to a rolling boil. What could have caused this premature clumpiness? One tantalizing lead points to primordial gravitational waves, ripples in spacetime from the universe's violent birth. These waves might have acted like cosmic fingerprints, imprinting their patterns onto matter during the Big Bang, creating dense regions where galaxies would later flourish and empty stretches where nothing took root. Another possibility involves quantum fluctuations, those microscopic hiccups in the fabric of reality. In the first fractions of a second, these tiny tremors could have been stretched to cosmic proportions by inflation, becoming the seeds for the universe's uneven structure. But here's the twist: some of these voids and filaments are too extreme, too sharply defined to fit even those explanations. The coldest, emptiest regions stretching hundreds of millions of light years with barely a galaxy in sight shouldn't exist in today's models. It's like finding a desert the size of a continent where the map promised fertile land. And the filaments, they're not just threads, they're colossal rivers of galaxies, flowing along invisible highways of dark matter, far thicker and more pronounced than simulations predicted. Now shift focus to the too-cold gas clouds, another cosmic anomaly. Floating in the depths of intergalactic space, these frigid pockets of hydrogen are so chilly they defy the ambient warmth of the early universe. Conventional physics says they should have been warmed by the residual heat of the Big Bang or the first starlight, yet they linger at temperatures barely above absolute zero. It's like finding ice cubes in a sauna, something's keeping them frozen against all odds. One radical theory suggests these clouds are cosmic relics, regions where dark matter's pull created natural refrigerators. Picture dark matter's gravity acting like an invisible shield, sheltering gas from external heat while allowing it to radiate energy away into space. Or perhaps these cold zones are shadows cast by primordial black holes, their gravity bending radiation around them, leaving behind pockets of unexpected chill. The implications are staggering. If matter clumped this unevenly and gas stayed this cold, the early universe wasn't just a mild-mannered nursery for galaxies. It was a place of extremes, where the rules of thermodynamics played out in ways we're only beginning to decode. And if we're missing something fundamental about how structure formed, it might mean our understanding of dark matter, inflation, or even gravity itself is incomplete. Which brings us to the next revelation. These cold clouds might be more than cosmic oddities. They could be time capsules, preserving the pristine chemistry of the universe's infancy in a way no laboratory ever could. Inside them, the original ingredients of creation might still linger, untouched by the furnaces of stars or the violence of galactic collisions. Unlocking their secrets could rewrite the story of how everything began, not as a uniform sea of matter, but as a dynamic, chaotic canvas where light and shadow danced to a rhythm we're only now beginning to hear. The coldest places in the universe shouldn't exist, at least, not where we've found them. Floating between galaxies, these ancient hydrogen clouds hover just a few degrees above absolute zero, colder than the deepest voids of modern space. According to every model, they should have been warmed by the afterglow of the Big Bang or the first starlight, yet they cling to their chill like cosmic ice cubes refusing to melt. This isn't just a minor discrepancy, it's a thermodynamic revolt, forcing us to confront the possibility that something invisible is actively cooling the universe's primordial fuel. So what's playing cosmic refrigerator? Dark matter is the prime suspect, but not as we know it. Most theories treat dark matter as a passive scaffold. It's gravity shaping galaxies, but otherwise indifferent to the gas around it. But these frigid clouds suggest a more intimate relationship. Imagine dark matter particles not just drifting through space, but interacting with hydrogen in exotic ways, colliding with atoms like ghostly snowflakes, sapping their heat with each encounter. Some models even propose dark matter could emit its own form of radiation, invisible to our telescopes but carrying energy away into the void, leaving the gas colder than it has any right to be. Then there's the wild card, undiscovered particles. The early universe might have been teeming with speculative entities like actions or sterile neutrinos, weightless, nearly invisible particles that could have acted as heat thieves, stealing thermal energy from ordinary matter without leaving a trace. Picture a cloud of hydrogen surrounded by these phantom coolants, its warmth siphoned away by interactions we can't yet detect. It's like standing in a room that grows colder for no reason, while something just beyond your perception quietly opens a window to the void. The implications are staggering. If dark matter or new particles are cooling these clouds, they're not just passive ingredients in cosmic evolution. They're active architects shaping the universe's structure by controlling where and when gas can collapse into stars. Cold gas forms stars more easily, too cold, and it might freeze into immobile clumps, stifling galaxy growth entirely. This could explain why some regions of the early universe remained barren, while others blossomed with galaxies, a cosmic divide etched by unseen hands tinkering with temperature. But here's the twist: these icy clouds might be more than cosmic oddities. They could be time capsules preserving hydrogen in its primordial state, untouched by the furnaces of stars or the shockwaves of supernova. Locked within them could be clues about the universe's first moments, a pristine record of conditions before light conquered the darkness. Decoding their secrets wouldn't just solve a thermodynamic puzzle. It might rewrite the story of how the cosmos assembled itself from the cold ashes of the Big Bang. Which brings us to the next revelation. If something's cooling the universe's fuel, what else is it building in the shadows? The answer might lie in structures so vast they defy comprehension, cosmic scaffolding woven from dark matter's invisible threads. We always assumed the universe's grand structures, galaxies, clusters, the cosmic web itself, were built by ordinary matter, the stuff we can see and touch. Baryons, the particles that make up stars and planets, were supposed to be the master architects, but dark matter never got the memo. New simulations reveal a bizarre possibility. What if dark matter wasn't just a passive scaffold, but an active sculptor, crafting invisible, dark stars, or even entire dark galaxies that guided the growth of everything we see? This isn't just a tweak to the story, it's a cosmic paradigm shift, suggesting we've been staring at half the blueprint all along. Picture a dark star. Not a dead husk like a neutron star, but something far stranger, a hypothetical object powered not by nuclear fusion, but by the annihilation of dark matter particles colliding in its core. These phantom suns could have burned with eerie, invisible light, their gravity warping the gas around them, funneling it into the first galaxies like cosmic magnets. Unlike normal stars, they wouldn't radiate heat or light, just a subtle gravitational pull, bending the visible universe to their will. Simulations show these dark stars might have been monstrous, dwarfing even the largest supergiants, their influence stretching across hundreds of light years. And here's the kicker: some could still exist today, lurking unseen in galactic halos, their presence betrayed only by the way they twist space-time around them. Then there's the idea of dark galaxies, structures made entirely of dark matter, devoid of stars but teeming with gravitational might. These invisible islands could have acted as cosmic waypoints, their gravity steering streams of gas into the filaments of the cosmic web. Without them, the universe's large-scale structure might look entirely different, like a spiderweb missing half its threads. Some astronomers even speculate that these dark galaxies outnumber visible ones, a hidden majority shaping the cosmos from the shadows. The proof: peculiar gas clouds that move as if tugged by unseen hands, or dwarf galaxies with far too few stars for their apparent mass, hinting at dark matter's invisible architecture. But the real mind-bender is how this changes the timeline. If dark structures formed first, they could have provided ready-made gravitational wells for ordinary matter to collapse into, jump-starting galaxy formation eons earlier than we thought. That would explain why some galaxies appear impossibly mature in the early universe. They had a head start courtesy of dark matter's hidden blueprints. It also raises a haunting question. What if dark matter isn't just a backdrop, but the true conductor of cosmic evolution, with visible matter merely playing along? This brings us to the paradox of early cosmic magnets, another piece of the puzzle that doesn't fit. Some of the universe's oldest galaxies show evidence of powerful magnetic fields, far stronger than current models can explain. These fields shouldn't have had time to grow so intense so soon, unless something amplified them. Could dark matter's unseen currents have played a role? Theorists are now exploring whether dark particles, if they carry even a faint electromagnetic charge, could have generated these fields through motions we can't detect. Or perhaps the turbulent birth of dark stars whipped primordial plasmas into magnetic frenzies, imprinting their fingerprints on the cosmos before the first true stars even ignited. One thing's clear: the universe's construction crew was far more diverse than we imagined. Baryons might have built the walls, but dark matter laid the foundations, and we're only beginning to glimpse the invisible hands that shaped everything. Magnetic fields were never supposed to be this strong in the cosmic dawn. Conventional wisdom painted the early universe as an electromagnetically quiet place, a vast, unmagnetized void where the first stars flickered to life without the invisible scaffolding that shapes modern galaxies. But when astronomers trained their instruments on some of the oldest galaxies ever observed, they stumbled onto a cosmic paradox: magnetic fields as powerful as those in mature galaxies today, threading through infant star systems like ghostly wires. These fields shouldn't exist. They defy every model of how magnetism grows, leaving scientists scrambling to explain how such intense forces emerged when the universe was still in its infancy. The numbers don't add up. In today's galaxies, magnetic fields strengthen gradually over billions of years, amplified by the slow churn of gas and the dynamo effect of rotating stars. But these primordial galaxies, their magnetic fields are already fully formed, as if someone hit fast forward on cosmic evolution. One explanation is as radical as it is elegant: the universe might have come pre-magnetized. Imagine the Big Bang not just as a fireball of particles, but as a cauldron of primal electromagnetic energy, imprinting magnetic seeds into the fabric of spacetime itself. These primordial fields, weak at first, could have been stretched and amplified by the universe's expansion, woven into the cosmic web like invisible threads. Then there's the black hole wildcard. Some theorists suggest supermassive black holes acted as cosmic electromagnets, their violent accretion disks generating powerful jets that magnetized surrounding gas at breakneck speeds. Picture a quasar's jet, a particle accelerator the size of a galaxy spewing magnetized plasma into the void, electrifying entire neighborhoods of space in a single outburst. But even this dramatic scenario struggles to explain the sheer scale of the magnetism we're seeing. These fields aren't just localized, they're galaxy-wide, implying a coordination that shouldn't have been possible so soon. Here's where dark matter might rewrite the script. If dark particles carry even a faint electromagnetic charge, or interact with normal matter in ways we haven't detected, their motions could have generated magnetic fields indirectly. Picture dark matter halos swirling around early galaxies like invisible whirlpools, their subtle currents stirring up magnetic turbulence in the gas they enveloped. Or perhaps the universe's first stars were far more efficient at seeding magnetism than we realized, their explosive death scattering magnetized debris across cosmic distances in a single generation. The implications ripple far beyond magnetism. If fields were this strong, they would have shaped how gas collapsed into stars, how galaxies rotated, even how cosmic rays traveled through space. Star formation might have been funneled along magnetic lines, creating orderly stellar nurseries instead of chaotic bursts. Galactic winds, those torrents of gas blown out by young stars, could have been guided by these invisible rails, sculpting the cosmos in ways we're only beginning to map. Now, shift focus to another cosmic anomaly, the early universe's embarrassing abundance of massive galaxies. Theory said they shouldn't exist, at least not in the numbers we're seeing. Simulations predicted a sparse population of modest galaxies in the cosmic dawn, growing slowly through mergers. Instead, telescopes like James Webb keep finding colossal, fully formed galaxies lurking in the ancient cosmos, as if the universe skipped the tutorial and jumped straight to advanced mode. The problem isn't just their size, it's their sheer sophistication. These galaxies aren't just big, they're already settled into elegant disks and bulges, their stars aged and their black holes monstrous. It's like stumbling onto a medieval castle in what should be the Stone Age. The leading theory, a hidden fast track to galaxy growth. Maybe the first gas clouds collapsed more efficiently than we thought, bypassing the usual mergers and forming monolithic giants in one swift collapse. Or perhaps dark matter's hidden scaffolding was unusually dense in certain regions, funneling gas into galaxies at speeds that left simulations in the dust. But here's the twist: these galaxies might not be loners. Some could be part of unseen clusters, their apparent isolation an illusion caused by faint companions lurking just below detection thresholds. If true, it would mean the early universe wasn't just building galaxies, it was assembling entire metropolises in cosmic blink. And that raises an even deeper question. If magnetism and mass conspired to jumpstart the cosmos, what other shortcuts did the universe take to become the rich, structured place we see today? Massive galaxies weren't supposed to throw cosmic temper tantrums, especially not when the universe was still in diapers. According to every textbook, giant galaxies like our Milky Way took billions of years to assemble through countless mergers, a slow accumulation of stars and gas that mirrored a city growing brick by brick. But the James Webb Space Telescope just caught a group of celestial toddlers, red-handed colossal galaxies, already fully formed when the universe was just a few 100 million years old. These aren't just precocious overachievers, they're cosmic rule breakers, flaunting sizes and maturity that should have taken eons longer to achieve. Let's put this into perspective. One of these ancient behemoths, spotted when the universe was barely 2% of its current age, contains as many stars as the Milky Way, except it packed them all together in a space 10 times smaller. Imagine squeezing New York City's population into a single neighborhood, then realizing this urban sprawl existed before the invention of the wheel. The numbers defy every simulation based on hierarchical growth, the idea that galaxies start small and grow through mergers. So how did these giants cheat cosmic evolution? One radical theory suggests mergers happened at warp speed in the early universe. Picture a demolition derby where cars don't just collide, they fuse instantly, creating ever larger vehicles with each crash. In the dense, hot environment of the cosmic dawn, gas-rich galaxies might have merged so violently and frequently that they skipped the usual growing pains, vaulting straight to maturity in a fraction of the expected time. Dark matter could have turbocharged this process if its halos were unusually dense, their gravity would have dragged galaxies together like magnets in a cosmic junkyard. But there's an even wilder possibility. What if some galaxies didn't grow from the bottom up at all? The top-down formation theory proposes that certain galaxies collapsed all at once from enormous, pre-existing gas clouds, like a single massive raindrop forming instead of countless tiny droplets. In this scenario, pristine hydrogen and helium clouds, cold and dense beyond anything in today's universe, could have fragmented directly into giant galaxies without first forming smaller pieces. It's the difference between building a skyscraper floor by floor versus having the entire structure materialize in one miraculous instant. The implications rewrite cosmic history. If top-down formation was common, the early universe wasn't just a scaled-down version of today's cosmos. It operated under fundamentally different rules, with physics we're only beginning to decipher. Gas might have flowed along dark matter's hidden highways with terrifying efficiency, pooling into ready-made galactic giants while bypassing the usual stages of growth. And here's the kicker. If galaxies formed this way, their stars would have different chemical fingerprints born from purer, less recycled material than stars in modern galaxies. That means some of the universe's oldest stars might be hiding in plain sight, their origins masked by later mergers. Now, brace for the next curveball. These ancient giants aren't just big, they're bizarrely structured. Some show fully formed disks and spiral arms when they should be chaotic blobs, their symmetry defying the turbulence of the early cosmos. Others host supermassive black holes that are proportionally too large, as if the galaxies grew around pre-existing gravitational monsters. It's like finding a perfectly baked loaf of bread in what should be a raw lump of dough, a violation of nature's expected sequence. Which forces the ultimate question: if the rulebook was this different in the cosmic dawn, what other chapters of cosmic evolution have we been reading wrong? The answer might lie in the most unexpected places, not in the galaxies we can see, but in the invisible currents of dark matter that shaped them from the shadows. We've always pictured the early universe as a vast, unbroken expanse, a smooth, featureless sheet stretching endlessly in every direction. Geometry was supposed to be straightforward, flat as a tabletop, with space obeying the tidy rules of Euclid. But the cosmic microwave background, the oldest light in existence, is whispering something far stranger. Tiny, unexplained fluctuations in this primordial glow hint that the universe's geometry might not have been so simple after all. Some patches appear stretched or compressed in ways that defy flatness, as if space itself were subtly warped or even folded like origami in those first moments. This isn't just about curvature. The real shocker: the universe might have been multiply connected, a cosmic Möbius strip where traveling far enough in one direction could theoretically bring you back to where you started. Imagine space not as an infinite plane, but as a hall of mirrors with hidden loops and twists woven into its fabric. Topologists call these shapes compact manifolds, and if they existed in the early cosmos, they'd leave fingerprints in the microwave background, strange, repeating patterns where large-scale structures align in ways that shouldn't be possible in a simple, infinite universe. So where's the evidence? Look no further than the so-called cold spot, a bizarre, galaxy-free void in the cosmic microwave background, chillingly colder than its surroundings. Standard inflation theories can't explain its size or temperature, but if space were multiply connected, this anomaly might be a ghostly echo, a place where the universe's topology folded back on itself, creating a lensing effect that drained energy from that patch of sky. Even wilder, certain statistical quirks in the microwave background's fluctuations align eerily well with predictions for a dodecahedral space, a 12-sided shape where opposite faces connect seamlessly. It's like finding the seams in a cosmic soccer ball, but here's the twist. If the universe was curved or knotted early on, where did that geometry go? Inflation, the exponential expansion thought to have occurred fractions of a second after the Big Bang, should have ironed out any wrinkles, stretching space so flat that curvature became negligible. Unless, of course, inflation didn't work quite the way we think. Some models suggest that quantum fluctuations during inflation could have locked in primordial topology, preserving traces of it like fossils in spacetime. Or perhaps dark energy, the mysterious force accelerating the universe's expansion today, is subtly resurrecting those early curvatures, warping space on scales we're only beginning to detect. Now shift gears to the universe's missing energy. Even if we account for all known matter and dark energy, the math still doesn't balance. The cosmos seems to be holding back, like a runner conserving stamina for a sprint we can't see. One radical explanation ties back to topology. If the universe's shape isn't what we assume, our calculations for its total energy could be wildly off. Imagine trying to measure the water in a twisted hose. Without knowing its loops, you'd never guess the true volume. Similarly, hidden cosmic folds might be hiding energy in plain sight, redistributing it in ways that skew our observations. The implications are staggering. If the universe's geometry was mutable, even briefly, it could rewrite our understanding of inflation, dark energy, and the very nature of space-time. Perhaps the cosmos didn't start with a single, simple shape, but cycled through phases of curvature like a celestial kaleidoscope, each twist imprinting new patterns on the fabric of reality. And if topology holds the key to the missing energy crisis, we might be on the verge of solving two cosmic mysteries with one revelation: that the universe, in its infancy, was far more intricate and interconnected than we ever dreamed. Which raises the next question: if geometry wasn't fixed, what else about the early cosmos was fluid? The answer might lie in a force so pervasive we rarely notice it until it vanished without a trace. Energy budgets in the cosmic dawn were never supposed to look like an accountant's nightmare. According to the textbooks, the early universe played by strict thermodynamic rules, energy in balanced neatly against energy out, with every photon and particle accounted for. But the cosmos has a knack for creative bookkeeping. Recent observations reveal glaring discrepancies in the energy ledger of the universe's first epochs, with some regions radiating far more energy than their visible sources can explain, while others sit in baffling deficit, like cosmic dead zones drained of power. These anomalies aren't just rounding errors, they're screaming clues that something fundamental is missing from our equations. Take the case of ancient quasars, those brilliant beacons powered by supermassive black holes. Their light, analyzed by telescopes like James Webb, carries traces of ionized gas that shouldn't exist so early. To rip electrons from hydrogen atoms in such quantities requires staggering energy, except the quasars themselves don't emit enough ultraviolet radiation to do the job. It's like finding a scorched forest with no sign of a fire. The numbers demand an unseen energy source, something pumping extra power into the system. Could this be dark energy's debut, flexing its muscles long before it supposedly dominated the cosmos? Or perhaps something more exotic, decaying fields from the inflationary epoch, remnants of the Big Bang's explosive birth, finally releasing their pent-up energy in bursts that lit up the cosmic dawn like phantom fireworks. Then there are the voids, those vast, empty regions between galaxies where the energy deficit is even more puzzling. Gas in these deserts is colder than models predict, as if some invisible siphon is draining heat away. Dark matter might be the culprit, but not in the way we imagined. If certain dark particles interact weakly with photons, they could act like cosmic sponges, absorbing energy and redistributing it invisibly. Or consider the radical possibility of shadow photons, hypothetical particles from a parallel sector of physics, leaking energy into or out of our universe through hidden dimensions. The real shocker, this energy imbalance might explain one of the cosmic dawn's biggest mysteries: early cosmic pollution. Heavy elements like carbon and oxygen, forged in the hearts of stars, are showing up in gas clouds far older than they should be. Traditional models say these elements needed generations of stars to live, die, and scatter their ashes. But if unknown energy sources turbocharged star formation, or if exotic particles catalyzed nuclear reactions directly, the universe's chemistry could have gotten a head start. Picture a primordial gas cloud, zapped by energy from a decaying field, suddenly fusing hydrogen into heavier elements without waiting for stars to form. It's alchemy on a cosmic scale, and the fingerprints are everywhere. Now pivot to the pollution paradox. Some of the earliest galaxies are dustier than a medieval attic, their light reddened by thick clouds of carbon and silicon particles. This isn't just surprising, it's borderline impossible. Dust requires generations of stars to live and die, yet these galaxies appear too young to host such prolific dust factories. Unless, of course, the universe had a shortcut. One tantalizing theory points to supermassive stars, hundreds of times heavier than our Sun, that lived fast and died violently, their explosive death spewing dust directly into space within a few million years. Or perhaps the dust didn't come from stars at all. Quantum fluctuations in the early universe might have directly assembled microscopic grains in the turbulent aftermath of the Big Bang, like soot condensing in a cosmic chimney. The implications rewrite the story of life's building blocks. If heavy elements and dust were abundant this early, the first planets and the chemistry for life might have arisen in a cosmic blink. No longer is the cosmic dawn a sterile prelude. It becomes a vibrant, messy era where the universe rushed headlong toward complexity, fueled by energies and processes we're only beginning to glimpse. And if dark energy or exotic particles were the unseen architects of this acceleration, their influence didn't just shape the past, they're still shaping the cosmos today, hidden in plain sight. The cosmic dawn was supposed to be a blank slate, a sterile expanse of hydrogen and helium, untouched by the complex chemistry that would one day brew the building blocks of life. But the universe, it seems, had other plans. Astronomers peering back to the universe's first billion years have stumbled onto something astonishing. Galaxies already choked with dust grains and complex molecules, their light tinged with the spectral fingerprints of carbon, silicon, and even water. These aren't just trace amounts, they're thick, swirling clouds of cosmic grime, as if the universe rolled up its sleeves and started cooking chemistry before the first stars had even finished blinking into existence. Think about what this means. Dust, those tiny flecks of carbon and silicates, should take generations of stars to produce. Stars must live, die, and scatter their ashes into space, enriching the cosmos with heavier elements over billions of years. Yet here we are, finding galaxies barely out of diapers already coated in soot, their light dimmed by vast dust lanes that have no business existing so soon. It's like walking into a bakery 5 minutes after it opened and finding the shelves piled with freshly baked bread. The timeline just doesn't add up. So how did the universe get so dirty so fast? One possibility is that the first stars didn't just die, they exploded with unprecedented violence, hurling their guts across space in supernovas so powerful they skipped the usual steps of stellar recycling. Picture a star 100 times more massive than our Sun, its core collapsing not into a neutron star, but into a black hole with such ferocity that it shreds the star's outer layers into dust in a single catastrophic blast. These pair-instability supernovas could have been the universe's first industrial-scale polluters, spewing heavy elements and dust directly into the void in quantities that would take modern stars eons to match. But there's an even wilder idea. Maybe dust didn't come from stars at all. Quantum fluctuations in the seething plasma of the early universe might have directly assembled microscopic grains, like soot condensing in the wake of a cosmic fire. Or perhaps dark matter played a role, its mysterious interactions catalyzing the formation of complex molecules in ways we haven't yet imagined. Some theorists even speculate that primordial black holes, evaporating via Hawking radiation, could have left behind clouds of exotic particles that decayed into dust. The implications are staggering. If complex chemistry was already underway in the cosmic dawn, the timeline for life's potential stretches back further than we ever dared dream. Carbon, oxygen, nitrogen, the raw materials of DNA and proteins weren't just present. They were already mingling in cosmic clouds, dancing toward complexity while the universe was still in its infancy. Imagine a planet forming around one of the first stars, its surface sprinkled with water and organic molecules billions of years before Earth even existed. The idea that life's ingredients were available so early forces us to confront a humbling question. Could biology have gotten a head start in the universe's forgotten eons? And here's the twist that changes everything. If life's building blocks were this abundant this early, then the story of life on Earth might not be special, it could be late. The universe may have been seeding the possibility of life since the cosmic dawn, setting the stage for countless experiments in biology we've yet to discover. The search for life's origins just got a lot bigger, and the cosmic clock just got a lot more interesting. We've always drawn a sharp line between the cosmic dawn and the epochs that followed, as if the universe flicked a switch, transitioning neatly from darkness to light, from simplicity to complexity. But nature rarely respects human-made boundaries. The latest observations reveal a startling truth. The cosmic dawn wasn't a clean break, but a lingering twilight, its echoes bleeding into later eras like colors blending at sunset. This isn't just a tweak to the timeline, it's a fundamental rewrite of how we periodize cosmic history, forcing us to confront the messy, overlapping rhythms of a universe that refuses to be boxed in. Take reionization, the process where starlight burned away the primordial hydrogen fog. Textbooks paint it as a definitive curtain call for the cosmic dawn, a milestone that ushered in the universe's adolescence. Yet when astronomers mapped the distribution of ionized gas across billions of light years, they found something peculiar. Patches of the cosmos still shrouded in neutral hydrogen long after reionization was supposed to be complete, while other regions had cleared shockingly early. It's as if the universe couldn't agree on when the party was over, with some neighborhoods clinging to the past while others raced ahead. This isn't just a matter of cosmic laggards. It suggests the processes we associate with the cosmic dawn, like star formation and black hole growth, operated on staggered clocks, their effects rippling across epochs we'd assumed were distinct. Then there's the chemical evidence. The first stars were supposed to be pure, crafted solely from hydrogen and helium, their compositions untainted by heavier elements. But when astronomers analyzed light from galaxies dating to the supposed end of the cosmic dawn, they found traces of carbon and oxygen where none should exist. These elements, forged in stellar furnaces, imply that second or even third generation stars were already shining while the last vestiges of the dawn still clung to the cosmos. The eras didn't just overlap, they danced, with the universe's chemical enrichment beginning even as the first starlight still struggled to pierce the darkness. Here's where it gets even stranger. Some of the oldest supermassive black holes we've detected, those cosmic anomalies that grew too big, too fast, appear to have continued their explosive growth well into what we consider the post-dawn universe. Their feeding frenzies didn't align with the timeline. They spilled across the boundary, dragging cosmic dawn physics into later epochs like a guest who overstays their welcome. This blurring of phases suggests that the mechanisms powering the dawn, perhaps exotic dark matter interactions or primordial density fluctuations, didn't just vanish when we thought they did. They lingered, shaping galactic evolution long after their curtain call. The implications are profound. If the cosmic dawn wasn't an isolated chapter but a prologue that refused to end, our entire narrative of cosmic evolution needs reworking. Structure formation, chemical enrichment, even the emergence of magnetic fields, all these processes might have operated on continuums we're only beginning to trace. It's like discovering that childhood didn't end at adolescence, but that its rhythms and influences wove themselves into adulthood in ways we never noticed. This realization forces a humbling question. What other cosmic eras are merely illusions, artifacts of our desire to categorize a universe that flows like a river rather than ticks like a clock? The answer might lie in the next great observatories, whose lenses could finally show us the universe not as a series of snapshots, but as the seamless, unruly masterpiece it truly is. The cosmic dawn wasn't just an era, it was a revolution, a cosmic coming-of-age story where the universe threw out the rulebook and rewrote physics on the fly. Think about it, black holes that grew faster than thought possible, galaxies that matured like prodigies, and starlight that didn't just flicker on. It exploded in chaotic bursts as if the cosmos couldn't wait to shine. Every assumption we held about this primordial epoch has crumbled under the weight of new data, revealing a universe far more inventive, more unpredictable, and frankly, more alive than our models ever allowed. Take those supermassive black holes, for instance. They weren't supposed to exist so soon, yet there they were, cosmic titans already in place when the universe was barely a toddler. Or the galaxies that defied all expectations, flaunting intricate spirals and bustling stellar nurseries long before they should have had the time to develop them. Even the darkness itself played tricks on us, with patches of the early universe inexplicably colder or hotter than the rules allowed, as if some unseen hand kept tweaking the thermostat. And let's not forget the greatest lesson of all: the universe hates uniformity. It didn't wake up gently. It erupted in fits and starts, with some regions racing ahead while others lingered in shadow. Light didn't spread evenly, it punched through like a boxer, leaving holes where it pleased. Stars didn't form in solitude, they clustered in frenzied families, their collective brilliance rewriting the timeline of cosmic dawn. Everywhere we look, the cosmos thrived on chaos, thriving in the messy, the uneven, the gloriously unbalanced. So what does this mean for us? It means the universe is still full of surprises, and every answer we uncover only leads to deeper questions. The cosmic dawn wasn't just a chapter in a textbook, it was a declaration that the cosmos refuses to be tamed by our equations. And with next-generation telescopes set to peer even further back, who knows what other cosmic rule-breakers we'll find lurking in the shadows? Which of these revelations left you speechless? Was it the black holes that defied time, the galaxies that grew up too fast, or the eerie cold spots that shouldn't exist? Drop your thoughts in the comments. We're all part of this ongoing discovery. And if you're as captivated as we are by the universe's endless creativity, don't forget to subscribe. The story of the cosmos is far from over, and the next chapter might just rewrite everything we think we know again.